Hello everyone and welcome to this video. In this session I'm going to write a simple Python program to solve a system of equations for what we call a compartment model. In epidemic we call our models as compartment models, with the population under study being divided into compartments and with the assumption about the nature and time rate of transfer from one compartment to another. So basically one of the models, what we call is SIR model. S stands for susceptibles, I stands for infected, and R stands for recoveries. We use this terminology to describe a disease which transfers from susceptibles, individuals in the compartment as susceptibles, to the infective class, and then from infective class some people recover and some unfortunately die. There are other models like SIS models. This type of models confers that there is no immunity against reinfection, but it means that once the person is infected, in this model we consider that once the person is infected it cannot be infected again. Once it's recovered it cannot be infected again, but in SIS models actually the person who is infected and then recovered can be infected again. We have other models like SEIR and SEIS models, which consider the exposed periods between being infected and becoming infective. So these models you can go ahead and search for yourself and start implementing it. So we will solve this SIR model by formulating it with differential equations. So differential equations that we have are these three differential equations. The first one is the rate of change of susceptible people. The second one is rate of change of infective people. And R dots represent the recovery rate. Now the first differential equations basically says that an average member of the populations makes contact sufficient to transmit infection with the rate of beta n. Beta is a constant which represents the contact rate, and n represents the total population under study. The second one says that infective leaves the infective class at the rate alpha I per unit time. So alpha again is the rate for recovery. And the third equation is the rate of change of recoveries. So once the person is susceptible and infected, it cannot go back again to susceptible class. It should leave this class and come to the class of recoveries. And the sum of susceptibles are infective and recoveries should be always equal to n. So we get started and solve our equations numerically. First of all, I need to import three libraries: NumPy, SciPy, and Matplot library to plot my results. I will use from SciPy library ODInt function to solve the system of equations. First of all, I need to define my variables. So in this case, my variables will be n, I, and s. So the n, total population, here I have considered n as 1000, and then I0 and S0 as the initial values. I have considered 1 for initial value for I0. Of course, there is always one person who starts the epidemic, gets infected, and S0 is n minus 1. So I subtract the I0 from the total population n. And R0 is the number of recoveries. Of course, in the first day, there is no recovery, so R0 in our case is 0. Then I define the contact rate beta and recovery rate alpha. beta, I have considered it as 0.1. I can change it, for example, to 0.2. And recovery rate in units of days, 1 over days is 1 over 15, which says that in 15, every person that who is infected can be recovered in 15 days. I go ahead and define an array for time from the day 0 to day 200. And here it comes, the definition of my differential equations, basically for S dot, I dot, and R dot. I write these equations. My independent variable is t, time, and my dependent variables are s, I, and r, which I have assigned it to y. And this function will return the s dot, I dot, and r dot. So if I initialize the conditions, so y0 with a vector, and then I can pass y0 and t to my ODE solver and get the result. So I run this cell. Now my ODE function is solved. I can get the results here. For example, for S, number of susceptibles starts from day 0, 999 and decreases to this number. The same goes for I, number of infected people. First day we have 1 and the last day is 0. And then I can plot these results. So this plot is quite important. However, this model is very simple, but it gives us very good insight over the system. The orange one, number of infected people, as you see, the number of infected people, the peak is 200, almost 300, let's say, and the peak reached in the day of 57, 60, let's say. And number of susceptibles start from 999 and decreases gradually over the time. The most important part is the contact rate. Actually, the contact rate is something that is defined kind of statistically. It's a bit difficult to calculate it very accurately because it depends on the society, it depends on the population's behavior and its habits. So if there is a community that they go out, they hang out a lot, they don't respect the quarantine rules, so this contact rate basically is increasing. So if we increase it from 0.2 to 0. Let's say 5 and run the cell, you'll see number of infected people gets increased. We have much more narrower peak. A number of susceptible people also starts and falls earlier. And if I reduce the contact rate to 0.15, you'll see that number of infected people, the peak is lower, and number of susceptibles also is higher in the final days. So it's a basic model, but basically what we can get as a preliminary idea is that we have to respect this quarantine rules, because clearly when the contact rate is increasing, number of infections is increasing, and we are putting in danger the lives of others. The second model that I would like to show you and solve it is with general contact rates. In the previous model, in the assumption of the previous model here, we considered beta as a constant. But it's a little bit unrealistic. What is more realistic is to assume a contact rate which is a non-increasing function of total population size. For example, in situation which the number of contacts per infective in unit time is constant. There are different models to capture this general contact rate. What we define as general contact rate is B with the B, which is a function of population, equals to C over N. There are different definitions for defining C. There are, what I found on the internet, there are 3 definitions for C. One model is this, with alpha n over 1 plus bn. There are the formulations. I will use the first one actually, but you can go ahead and blend the second and third model. So again, like another model, I will import my libraries. I will define initial population, I0 and S0. A stands for recovery rate, B stands for contact rate. I have defined it 0.2, and F, the definition of F is that a fraction F of the A alpha I members leaving the infective class at time t recover, and the remaining fraction 1 minus F die of disease. So basically here, if I define 0.9, it means that 10% of the population will die from the release. So if they die, it means that the number of the initial population will be decreasing. So because of this, in our formulation, instead of number of recoveries, we are using n, the rate of change of n. So again, we have a function, a system of differential equations, which we can solve them numerically. We don't include the rate of change of r here, because once s, I, and r is that s, I, and n is determined, we can calculate r just by the formula of n equals to s plus I plus r. So n is determined, s is determined, I is determined, and the only unknown variable is r, which we can extract it from our data. We go ahead and write our function, system of our differential equations. We initialize it with S0, I0, and 0, and we solve it by the function ODE_int of SciencePy package. And if I run this code, I get this graph, which is like before, number of infected people. I have here, one thing that I have done it here is that I have normalized my values. So my value is from 0 to 1, so it's a percentage actually here. So 40% of population is infected here. We have reached the peak. Here I can remove this over n0 and get the result for the total population. Yeah, so almost 500 people in the day 54 are infected, and the change in the population starts from 1000 and ends in the last day with the number of almost 900 people. So 100 people die from the disease. Again, like before, if we decrease or increase the contact rate, we will see the effect in the infected class of our compartment model. So I increase it to 0.4. And you see that number of the peak reaches a little bit in later, and the number of people with infection decreases. Actually, I can increase the time to 200, here 201, to get the peak. So you see here, the peak is almost in 240 in the day 123, and the mortality is n, our population is 916. So almost 84 people have died from this disease. Thank you very much for watching this video. It was a simple model. You can go search on internet, find more complex models, and try to solve it numerically.